Hello, everybody. Let's do the usual things. There's the chat. Okay. Let's see here. Sorry. Send you guys the usual things. Sorry, my stuff's all over the place. There's something else I want to throw in here. 1 second. Hopefully you guys are all doing all right. The reason I'm wearing headphones is because they're cutting pavers outside of my office window. It's super loud. They're not doing it right now, but I imagine they might start back up. So I'm wearing headphones with noise canceling, and it's kind of helping. But I will want you all to let me know if the noise gets unbearable, because it get pretty loud earlier, and I'm wondering if the microphone is going to pick all that up. So don't feel too bad. So here is the link to the usual attendance, tutoring, and then the third link there is a link to the fall quarter evaluation. If everyone could please fill that out when you have a chance, I would really appreciate it. So I'm fixing a few things here. Okay, there, nothing more normal. There's something else I wanted to grab for you guys. No, that's not it. Sorry, 1 sec. I guess I should ask, are there any questions you guys have? Anything you want to go over today? I see that Sanders says, yeah, Sanders has posted a new homework. It looks like, let's take a look at it. So it's a lot of finding critical points, finding the global maxes and mins. Now I will say, for the question he has for finding the global maximum and minimum, this question he actually asks where the global max and the global min are. So that's a question of what X is, not what Y is. Then there's, okay, some value theorem questions. Finding all critical points, find where the function's increasing, decreasing. Okay, well, look, so basically it's kind of all the stuff we do when we're graphing functions. So yeah, we can definitely go over that. Let me give you guys the links to the stuff again. And yeah. Okay. So I'll just kind of get started here. So I don't know if I told you I got new pens finally. It's pretty great. Make it nice and legible once again. All right, so let's go through the assignment and kind of just do questions like all the questions. And I'm just going to make up different functions. Okay. So, sure. Just trying to think. That's an interesting question. Okay. So for f of x equal to the square root of x cubed plus 8. Yeah. Where x is between, let's say, sure. Let's say -3 and 2. I want to find all the critical points, including the endpoints. That's interesting. Okay, sure. So to find the critical points, there are two things. Well, there's one thing I guess we do. There's two things we think about. So first, we, of course, we find where the derivative is equal to 0. So when someone says critical points or critical values, you should be thinking, oh, I'm going to set the derivative either equal to 0 or undefined. Both of those are placed directly. Now, they should be placed there in the domain of the original function. And this function, like the question number 1 on the homework, is defined everywhere, right? You can take the cube root of everything. Oh, sorry, the square root. Oh, actually, I take it back. This function is not defined everywhere, unlike the one on the homework. Let me change the domain just slightly here. Let's say the domain is -2 to 3. Sorry about that. So here, this function is defined everywhere on this interval. If I plug in -2, -2 cubed is 8, -8, -8 plus 8 is 0, square root is 0, 0. If the numbers were more negative, then this would be undefined at those places because of the square root. You like, if for example, if it was -3, -3 cubed is -27 plus 8 is -21. We can't take the square root of a negative number. So that's why I changed the domain. For the homework problem he gave you guys, which is the square root of x squared plus 21, that function is defined everywhere because x squared plus 1, sorry, square root of x squared plus 1, right, that function, since x squared plus 1 is always positive, there's never a place where that's going to be undefined. Okay, so I want to find the critical points, meaning I need to find the derivative. And if I'm going to find the derivative, I find it really, really helpful to rewrite the function as x cubed plus 8 to the 1/2 power. To me, it's just easier that way. So I'm going to take the derivative using the chain rule. The derivative of some stuff to the 1/2 power is 1/2 times my stuff to the -1/2 power times the derivative of this stuff, which is 3x squared. And now I'm going to try and find where this is equal to 0, but it's kind of funky. I really don't like negative powers. To me, they just feel they're a little bit challenging. So I would really rather write this as, let's see. So I'm going to have a 3x squared on top. And on the bottom, I have a 2 times an x cubed plus 8 to the positive 1/2. Or you could write the square root of x cubed plus 8 if you want to. So let me ask you guys, what value of x is going to make this equal to 0? And there is one correct answer here. Anybody?
Isn't it just 0?
Yeah, definitely 0. So I'm setting this equal to 0, I get x equal to 0. Now, what's going to make this undefined? Is there a value of x that's going to make this undefined? So specifically what I'm asking for is there a value of x that's going to make the denominator 0? In this case, the answer is also yes. Because if I plug in x equal to -2, -2 cubed is -8, and -8 plus 8 is 0. And the square root is 0, 0, so we'd be divided by 0. So here, x equal to -2 is also a critical value. And it's a real critical value in the sense that it's in the domain of the original function, right? -2, f of -2 is defined, and f prime of -2 is undefined. That is the kind of essence of being a critical value. In the domain, and the derivative has to either be 0 or undefined. So here are my critical values that I found from that. I got x equal to -2 and x equal to 0. And then I also have the endpoints, which I meant to make this less than equal to, sorry. So I also have my endpoints are -2 and 3. So my 3 critical values here are -2, 0, and 3. Are there questions about that? Also, here's the attendance and stuff again. Okay, so the second question asks about the first question. It says, find the location of the global maximum and the global minimum of this function. So to find the global max and the global min, so I should say to find the location of the global max and the global min, we need to find the x values where the function is either the largest or the smallest. So I'm going to take my critical points, -2, 0, and 3, and they're all in the interval, and I'm going to plug them into this function. So my function, which was the square root of x cubed plus 8, f of 0, f of -2, and f of 3. So f of 0 is going to be the square root of 0 cubed plus 8, which is just the square root of 8. F of -2 is going to be the square root of -2 cubed plus 8, which is going to be -8 plus 8, so the square root is 0, which is 0. And f of 3 is going to be the square root of 3 cubed plus 8, which is the square root of 27 plus 8 is 35. Okay, which of these three things is the smallest? 0, square root of 8, or square root of 35?
F of -2.
Yes, let's just, so you're right, it is f of -2, which is 0. And so we would say the global minimum occurs at x equals -2. Right? I believe that's the way he wants you to answer this location. I mean, so I suppose you could say it's there, or you could say at the point -2 comma 0. But I'm not sure if he wants the entire coordinate pair or just the x value. Just let's find the location. I think either way would be probably fine. So now, which is the biggest thing? Square root of 8, 0, or square root of 35? Clearly, square root of 35. And so we'd say the global maximum occurs at x equal to 3. Or at the point 3 comma root 35. And either way should be fine to answer it. Usually we just say where the what the x value is. Okay. So yeah, so question 1 and 2 on your homework are similar to this. You're just finding the critical values, and then you're plugging them into the original function to see what the biggest thing is and what the smallest thing is. So do make sure, right, when you're finding global maxes and global minimums, you're plugging things back into the original function. That's going to be different than finding relative maxes and relative mins, which we're going to start doing pretty soon. But you're not going to plug those values back into the original function. So problem 3 is asking about the mean value theorem. And the mean value theorem, so the mean value theorem in words says that, gosh, it really feels weird wearing these headphones with I know there's like no noise. So I'm gonna take these off, and I guess let me change my input real quick here. Sorry, one sec. I want, not that anyone's saying a whole lot, but that way if you guys say something, I should hear you, and then I'll put them back on if I need to later. So it was super loud here earlier. So the mean value theorem says, basically, if you have a function that's continuous, then the average rate of change of that function, somewhere in the life of that function, the actual instantaneous rate of change will be equal to the average rate of change. A better example or better description of that is if you're driving a car and you're not driving like cold jerky, so your speed your position is a continuous function, right? You're kind of just moving, and maybe you're going fast and you're going slow, but like the distance you are from some point is changing in a continuous way. Like maybe you're, right, if this is time and this is your position, and maybe you start off at 0, and then you're kind of driving slowly at first, so your position, right, you're not very far from wherever you started, but then maybe you speed up, maybe you slow down, then maybe you speed up, and maybe you slow down, right? But as you keep driving, your position just keeps getting further and further from whatever the 0 was. And so what we're saying here is that if this is representing your position, well, your average rate of change, your average speed, somewhere, at least one place in here, your actual speed has to be equal to the average speed. That's what the mean value theorem was saying. Somewhere in the interval, your average rate of, your actual rate of change has to be equal to your, or I should say your instantaneous rate of change has to equal your average rate of change. The thing I kind of think of, right, is I'm getting like a million phone calls this morning. It's kind of annoying. So let's say let's say I drove from Davis to the Bay Area, and let's say it took me 2 hours, and let's pretend it's, I don't know, let's say it's 100 miles, even though that's not really right. So let's say it took me 2 hours to drive 100 miles. And let's pretend like I never had to stop, right? Like I was able to, even if I was going slowly, I still was at least always moving forward. There was no stops on my trip. Traffic didn't come to a standstill. So that means my average speed, or my average rate of change, is 100 miles per 2 hours, which is equal to 50 miles per hour. And what the mean value theorem tells us is that if my average speed was 50 miles per hour, that means that somewhere, at least once on my drive, I had to actually be driving 50 miles per hour. I couldn't always be below 50 miles per hour, because otherwise my average would be 50. I couldn't always be above 50 miles per hour. And if I went from below to above, or from above to below, then I have to have actually gone 50 miles per hour, at least for one small moment. And maybe I drove 40 the whole time, and then sped up to 60 the other whole time, right? Right in there from 40 to 60, right? Somewhere I actually was driving 50 miles an hour. So that's very much the general idea of the mean value theorem, is that somewhere in this interval, the instantaneous rate of change is equal to the average rate of change. Now, graphically, here's what that looks like. This line, the slope of this line, is representing the average rate of change. And the slope of this tangent line, say right here, that slope is my instantaneous rate of change. And this pen is not looking excellent. And what we're saying here is that somewhere between here and here, this instantaneous rate of change has the same slope as this average rate of change. And it definitely looks like from the picture I've drawn that should be the case, right? That this line and this line are parallel, so they have the same slope. So that's kind of the whole idea. More formulaically, here's how it works. This is also, I should say, this is very much related to the intermediate value theorem, which I know we didn't talk about a whole lot in class, but I know he definitely covered it at one point. So here's the more general idea. If you've got a function, say f of x, and it's continuous on some interval from a to b, and differentiable on the same interval, except it doesn't have to be differentiable at the endpoints. If that's the case, then we have this kind of picture. I'm going to draw the picture first. So let's say we have, like, something like this, and sure, let's say this is A, and over here is B, and there's A f of A, and is B f of B. And then if we, so again, if we look at the slope of the line connecting these two things, this here, just had a bunch of others. I'm like, I have some new pens that I know are good. So if we look at this line connecting this here, the slope of that line is the average rate of change, but it's equal to the difference in the y's or the difference in the x's. And what the intermediate value theorem is saying is there's some point between A and B where the slope of the tangent line, looks like it's probably about right there, where the slope of this line is equal to that. The slope of this line isn't found this way, it's found by taking the derivative at this point C. So I know I'm kind of saying a lot, but it's kind of important. So the whole idea here is that the mean value theorem says that if f of x is continuous on a, b, and differentiable on the open interval a, b, then there has to be a number c between a and b such that the slope of the tangent line on the function at c is equal to the slope of the secant line connecting these 2 points, or such that f prime of c equals f of b minus f of a over b minus a. Okay, so I know it's kind of a lot, but again, I'm going to say the whole idea here is that if you've got a function, it's continuous and differentiable on the closed and open interval, then there has to be a point in between the endpoints where the derivative is equal to the slope of the points so the line connecting the endpoints. Okay, let's actually do a problem similar to problem 3. Where'd my eraser go? It's literally right there where it should be. I just, it's a Friday. It's week 8. Also, I wanted to mention 17. So for those of you thinking about taking 17B next quarter, whether that's if it's in fall, there is a 17B co-class. I don't think I'm going to be teaching. I think Sarah is going to be teaching it, which is great. Sarah's wonderful. I posted a link to the co-class stuff on the announcements in campus. So if you're looking for that information, whether it's for math, there's also chemistry stuff as well, somewhere around there. You can look there for that information. Also, darn, I believe there was something else I wanted to mention. No, I guess not. Here's the attendance and stuff again. I don't know. Oh, I was just gonna say, there's also, if you're planning on taking it over the summer, that's perfectly fine. Just be aware that we won't have co-classes, but all of the specialists will be available for office hours, and they'll probably be more available over the summer for office hours than we would be in the fall. So if you're thinking about doing it over the summer, we will certainly be around to help, just not in the same co-class way that we have been this quarter. All right, so let's say we have a function, and I'm just going to make something up. Let's say we have f of x equal to 2x cubed minus 5x squared plus 3x plus 1. Oh, that's this is probably not going to be wonderful. You know what? Life isn't always wonderful. So, and on the interval, now the nice thing about this function, this polynomial function, is it's defined everywhere. It's continuous everywhere. It's differentiable everywhere. Polynomials are great. Let's make the interval easy. Let's say we're on the interval from 0 to, let's go 3, seems maybe not too big. Okay, so what we want to do, and how does he phrase this? He said find a number c in the interval such that f prime of c is equal to the average. Okay, so we want to I usually say find all numbers c, because so the mean value theorem guarantees at least one such number, but it's actually possible to have multiple such numbers. So we're going to find all values c in the interval. And he writes it like this: c is an element of the interval from 0 to 3. And I think he writes it the right way. Yeah, I mean, technically it shouldn't be one of the endpoints, but that's fine. So find all values c in the interval from 0 to 3 such that f prime of c is equal to, and he writes it as f prime of c is equal to the average rate of change of f on the interval. So the average rate of change of f on the interval is the slope of the line connecting the endpoints. So that right there that I just wrote, that is the average rate of change of the function f on the interval from 0 to 3. Or as I would rather say, it's just the slope of the line connecting the points. Okay, so we have to find the derivative, plug in c, which is just going to, so let's find the derivative. right? The derivative here is not hard. It's going to be 6x squared minus 10x plus 3. So we're going to take that derivative. We're going to plug in c. So we're going to say 6c squared minus 10x plus, oh my god, minus 10c, sorry, plus 3. That's going to equal, so then we have to do f of 3 minus f of 0 over 3 minus 0. Hopefully it's not a terrible number. So let's see. Okay, I'm hoping this is going to come out to be all right. So let's see, f of 3 is 2 times 3. Yeah, you know what? Let's make our lives a little bit easier. Let's go 0 to 2. Just because 3 is just kind of a pain to plug in. It's not that bad, but okay. So we still, right, our derivative is still the same. Plugging in c is still the same. But now we're going to do f of 2 minus f of 0. So f of 2 is 2 times 8, 16, minus 5 times 4, which is 20, plus 3 times 2, which is 6, plus 1. That's f of 2 minus f of 0 is 0 minus 0 plus 0 plus 1. Super straightforward, over 2 minus 0. So we're trying to find all solutions to 6c squared minus 10c plus 3 equal to, let's see, 16 plus minus 20 is negative 4, plus 6 is 2, plus 1 is 3, minus 1 is 2, equals 2 over 2 equals 1. I simplified pretty nicely. So all of this here came out to be 1. So we're trying to solve 6c squared minus 10c subtract 1 plus 2 equal to 0. And if I was trying to solve this, I might try factoring it. It might factor. It probably doesn't factor. I don't know. I would just, so if I don't see that it factors right off the bat, I'm just going to jump straight to the quadratic formula. So I'm really hoping I get real numbers. I feel like I might have done something dumb and made something that comes out with imaginary answers, which would be terrible. No, actually, so you know what? I'm saying that, but I'm dumb. Because the mean value theorem guarantees that there is a value. So I can't get imaginary answers here because the mean value theorem says if you have this function and it's continuous and differentiable on the interval, and it definitely is continuous and differentiable, then there has to be a solution to this equation. So there has to be a real number c where the derivative here is equal to the average rate of change there. So I was worried that there wouldn't be an answer, but that was silly of me to be worried because there has to be an answer because it's a theorem that's been proven. If I was missing one of the conditions, like if this function were undefined somewhere, or if this function wasn't differentiable somewhere on the interval, then it would be okay to not get the answer. But since it meets all the conditions of the theorem, the result has to be true. So what I'm saying is there should be a solution here. So c is going to equal, let's see, negative 10 plus or minus the square root of negative 10 squared, which is 100, minus 4 times a times c, right? Not this c, but 6 times 2. Ooh, just barely going to get there, yeah. Oh, no, yeah. Over 2 times a. So we get c equal to 10 plus or minus the square root of, this is 100, and 4 times 6 is 24, times 2 is 48. 100 minus 48 is 52 over 12. Okay, so what have we got here? Oops, that's a 12. This actually is a good question. So I get c equal to 10 plus or minus the square root of 52 over 12, which is not a particularly nice number. You can simplify this a little bit. Square root of 52 is 4 times 13, so the square root of 52 is the square root of 4 times the square root of 13, which is 2. 10 to the square root of 13, so you get 10 plus or minus 2 root 13 all over 12. To be honest, I would get a calculator out here. And I would say, all right, I'm going to calculate 10 plus the square root. So here's what I'm thinking. 52 is close to 49. Square root of 49 is 7. This is a little bit more than 7. So 10 plus 7 is 17. 17 over 12 is bigger than 1 and less than 2. And that is in the interval, right? Whereas if you do 10 minus this 10 minus, no, they're both in the interval. So here's what I was trying to kind of hopefully point out. Oh, it's going to get loud again. I might have to put the headphones back on. If you get two answers, right, like you do here, only one of them has to be in the interval. If we check here, 10 plus the square root of 52, all of that, oh, that's okay, sure, divided by 12. Oh my God, I hate it. This calculator is cool, and then like we'll just write the thing and like reduce the fraction, but I actually want a decimal, so use the little equally button. It's about 1.43. So that is between 0 and 2. So definitely 10 plus 2 root 13 over 12 is one of the answers. But then the other one, 10 minus 2 root 13 divided by 12 is 0.232. And so that is also between 0 and 2. Now here's my bet. My bet is that the question he asked you for question number 3, I would imagine, no, his is probably easier. You probably only get one answer. So, but if you do get two answers, you need to check and make sure they're both in the interval, because sometimes only one of them is, but at least one of them has to be. Let me see if I can think of another example. Okay, yeah, I can think of an easy example. Can I think of an easy example? I thought I had one, and now it's gone. I guess I'm thinking of something like this. I'm gonna try to make this easy. Let's say f of x equal to x cubed on the interval from 0 to, I guess we can go to 2 again. So f of x is definitely continuous and differentiable on this interval. Now I want to find all c in the interval such that f prime of c is equal to the average rate of change, which is just another way of saying is equal to f of 2 minus f of 0 over 2 minus 0. All right, so let's solve this. So f of 2 minus f of 0 over 2 minus 0. Well, f of 2 is 8 minus f of 0 is 0 over 2 minus 0. 8 over 2 is 4. Okay, yeah, this one's going to work out. My derivative, f prime, okay, I'm going to put my headphones back on. Just one sec, sorry. You guys find the derivative while I do this. Let's see, I need to change the volume just in case you guys do happen to say something. I do like it when you talk. It's nice to hear your voices. So what's the derivative here?
(3x squared).
Thanks, Allison. Thanks for saying words. I appreciate it. And so then we're going to see where the derivative is equal to this. And there should be at least one value, maybe more, but at least one in the interval so that that's actually true. And sometimes people put in the c here. Sometimes people just solve with an x. It doesn't really matter if you use x or c. So we'll set 3x squared equal to 4. And we get x squared equal to 4/3. And then we take the square root. So x is going to equal plus 4 minus the square root of 4/3. However, we know since it has to be between 0 and 2, it has to be a positive number, so it can't be the negative one. So x equal to the positive square root of 4/3 is good, or I'd probably call it c at that point. That's the value that's actually in between, and x equal to negative square root of 4/3 is not what we wanted. So sometimes that happens with this mean value theorem kind of thing, where you get one that works out great and you get another one that does not. Okay. The mean value theorem is really important, especially when we start talking about antiderivatives and integrals. But aside from problems like this, question number 3 on the homework, there's not a lot of other great. I mean, there are a couple other interesting problems you can ask about it, but really, this is probably all you'll see of it until you start talking about 17b. But it definitely is important when you talk about how the integral is defined. Okay. Let's look at more stuff. I'm assuming we have something like, cool, yeah, so let's find critical points. Find all critical, I call them critical values usually. Critical values. I suppose the difference between critical value and critical point is the critical value is just the x value, whereas the critical point is probably the x and y coordinate. So it's probably actually more informative to find all the critical points. What do I want to do? Sure, let's do that. Okay. So I want to find all the critical points of this. So I'm going to take my derivative. Set it equal to 0. Well, first I'm going to take the derivative. So I have to use the quotient rule here. It's the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And now to be able to solve this, to be able to set this equal to 0 and solve it easily, we have to be able to simplify this thing. The numerator, the denominator is already as simplified as it's going to get, right? X minus 2 squared, you don't want to multiply that out, you just want to leave it as is. The numerator, on the other hand, we do want to multiply that because we got this minus this. We need to combine it so it's more simple. So I'm going to distribute the 2x here. You get 2x squared minus 4x minus x squared all over x minus 2 squared. And then I'm going to simplify this even further. 2x squared minus x squared is x squared minus 4x all over x minus 2 squared. And then finally, I can factor the top, I can factor in x. And look at x times x minus 4 over x minus 2 squared. Okay, so if I set this equal to 0, sorry. I set it equal to 0. What do I get for x when I set that equal to 0? What's one of the critical values?
0.
Yes, definitely. Okay, what's the other critical value?
4.
Yeah. Now, I'm going to leave it there for a second. So those are the critical values, and then I would say that the critical points are 0, f of 0 and 4, f of 4. That's kind of a lazy way of doing this. Be like, well, I know it's x, y, and the y value is just whatever you get when you plug in x. We should actually do this. If I plug in 0, right? F of 0 is 0 over negative 2. That's going to be 0, 0. And f of 4 is 4 squared, which is 16 over 4 minus 2, which is 2. 16 over 2 is 8. So those are my critical points. All right, so the question I want to ask, but it's really a trick question, is, am I missing any critical points? And the answer is no, I'm not. You might accidentally think that 2 is a critical value. So do we get, by saying this is undefined, do we get x equal to 2? Well, yes, x equal to 2 is a place where the derivative is undefined. But if you tried plugging 2 back into the original function, f of 2 is also undefined. So we can't have a critical point when x is 2 because there isn't a y value to go with it. Right? What we really have at 2 is the vertical asymptote. And we can't have a critical point or a critical value at a vertical asymptote. So 2 is not, x equal to 2 is not a critical value here. And it's really important to understand that if the function is undefined somewhere, there's no way we can have a critical value at that place where the function is undefined. Where did the 2x squared go? So I did 2x squared minus x squared and got 1x squared. Hopefully that clarifies that. Okay. This question's not great for the next question though. So what's up here? Give me 1 sec. So I just want to think of something here. Sorry, I'm just trying to come up with something cool. Cool being, relative. So I want 3x squared. That's boring. 3x squared plus 6x. Right, 3x squared, 6x minus 24. Let's say that's my function. That's not the function I wanted, sorry. That's the derivative I wanted. I wanted x cubed plus 3x squared. Sure. Minus 24x plus 8. So let's say that's our function. X cubed plus 3x squared minus 24x plus 8. And I want to find all the critical points. Now, right off the bat, unlike the previous problem, here I know there aren't any issues with the function being undefined. So whatever places I find where the derivative is either 0 or undefined, I'm going to get a critical value because the original function is defined everywhere. It's a nice polynomial. Polynomials are the best. They're continuous, they're differentiable, they're defined everywhere. Great. So we take the derivative. So actually, I want you guys to do this next part. So I want you to find the critical values. Take your derivative, whatever it might be, and set it equal to 0. I'll give you guys, we don't have a lot of time, so I'll give you about a minute to just work on that. How did I do that? All right, well, So there's I didn't even give you guys a minute. Sorry, we're almost out of time. So I mean, we have 8 minutes, but wanted to kind of get through this problem. So turn my on. So here's my derivative. I'm going to try to set that equal to 0. Now in this case, setting this equal to 0, I'm going to try and factor. And before I try doing like the factor, like x minus something, x plus something, I first just noticed that each of these actually has a factor of 3. Right, I've got 3 times x squared plus 2x minus 8. 8. And this factors as x plus 4 times x minus 2. So I can see that my critical values are x equal to -4 and x equal to 2. Or I could say my critical points are, playing this back in such a pain, right? -4, so I do really do this if I'm just feeling lazy. All right, -4 f of -4 and 2 comma f of 2. Right, those are my critical points. And yeah, I could plug in 2 and get 8 plus 12 is 20 minus 48 is -28 plus 8 is -20. So that one would be -20. This one, playing in -4 is worse. It's -64 plus 3 times 16 is 48. Minus 24 times -4 is plus 96. Plus 8, I don't know, it's -16, 8, it's 88. And yes, it is important to find those values, especially if you're going to be graphing this thing. You want to know what the y values are of your critical points. Then we want to ask, find the open intervals on which the function is increasing and decreasing. So here's the way you want to do this, in my opinion. It's really, really important to have your derivative and to have it factored as much as possible because that makes it easy to see what the sign of the derivative is. So when I'm finding where the function is increasing or decreasing, what I'm really doing is I'm finding where the derivative is positive or negative. If the derivative is positive, the function is increasing, which makes sense, right? Because if the function is increasing, the slope of the tangent line should be a positive slope. If the function is decreasing, right, it's going down, you're going to have a tangent line that's going to have a negative slope. So the derivative is going to be negative where the function is decreasing. So what we do is we make a sign chart for the first derivative. So I want to know what's the first derivative doing on the in general. And here's what we know: the function is the function's either positive or negative, and the only way you can change signs is by going through 0 or by going through undefined, which is why those are our critical points, by the way, right? We find where the derivative is 0 undefined because that's where the derivative can change signs. So this derivative, 3 times x plus 4 times x minus 2, is equal to 0 when x is negative 4 and when x is positive 2. So that means everywhere over here, it's got to be whatever the same sign it is, right? It can't change except until you get to 2. So if I pick a number larger than 2, like 3, and then plug it in, I get 3 times 7 times 1. I don't really care what the number is. I really care that it's a positive times a positive times a positive, which is positive. And if the derivative is positive, it means the function is increasing. And then you can do the same thing. You can pick a number between negative 4 and 2, like 0. And you see that it's a positive times a negative. So it's negative overall, which means the function is decreasing. And then you pick a number less than negative 4, like negative 5, and see that it's a positive times a negative, which is positive. So the function is increasing. So to answer the question, I would say, and now I should, so he might do this differently. This is something that I think should be done in a very specific way, but I think there's a textbook that does it weirdly. So I would say that the function is increasing on the open interval. So it's increasing here from negative 3 to negative 4. And I think you don't include negative 4, I use a parentheses. If he said use a bracket, then you should use a bracket. He's wrong. He's not wrong, it's just some books are weird and define things differently. And then I would also say it's increasing on the interval from 2 to infinity. So those are the intervals where it's increasing, or the interval where it's increasing. It's decreasing from negative 4 to 2. So it's increasing on the interval from negative 4 to 2. And that's how you would answer a question like that. Okay. And so I'm gonna skip ahead to those questions similar to question 7. So what we can then do with this, I just erased those. I didn't want to erase those. Sorry. My critical points were they were I think 2 and I think it was negative 8, was it? 8 plus 12 minus 48. I forgot.
Negative 20.
I think it was negative 20 actually. And then it was negative 4 comma, I think it's 88. I think that's right. Okay, so then what we can do is we can use the first derivative test with the sign chart to know if the function has a maximum or minimum. So at negative 4, the function is increasing, it gets to negative 4, and then it starts decreasing, which means at negative 4, we have a relative maximum. So we have a relative maximum at the point negative 4 comma 88, which means that at that point on the function, it's bigger than all the nearby points. Similarly, at negative 2, we see we are decreasing before negative 2 and then increasing afterwards. That means we have a relative minimum at the point 2, negative 20. So if I was going to start graphing this thing, here's what I would get. Let's see here. Sure. I don't know my x intercepts are because I picked a cubic function that I don't know how to factor in exactly. That's all right. Yeah. So I know I have relative max here and relative minimum here. So I have negative 488. There's my relative maximum. And a relative minimum at 2, negative 20. Like that there. So what this relative maximum is the function does something like this. And then this relative minimum is the function does something like this. I also want to have a y-intercept at 8. So I plug in the 0 for x, I get 8. So I'm going to hit the y-axis like that, maybe here-ish. So do something like this. Right, because the function is, before I get to negative 4, the function is always increasing. I get to negative 4, top out, and the function is decreasing from negative 4 until I get to positive 2. Then the function starts increasing again. And since it's increasing, decreasing, I have to have a maximum. Since it's decreasing, then increasing, I have to have a minimum. And I should say a relative maximum, relatively, because this is a relative maximum because while it's bigger than all the stuff next to it, it's not a global maximum, right? This function gets infinitely large. In a similar way, this point here is not a global minimum because this function gets infinitely negatively large. It's just a relative minimum. So this sign chart for the first derivative, I think, is the best way to determine if you have a relative max or relative minimum. If it's increasing, then decreasing, and you have a critical point, right, where the function is defined, then you have a relative max. If it's decreasing, then increasing, then you have a relative minimum. I know we're out of time, but give me 1 more minute, 2 more minutes, maybe, because I just want to show you one more thing. So remember how earlier we did this function? The function was x squared over x minus 2, and the derivative ended up being x times x minus 4 over x minus 2 squared. Yeah, that's what our derivative was. And our critical values were 0 and 4. So if I look at the sign chart here, well, there's an issue that negative 2 or positive 2, although it's not a critical point at 2, it's still a place where the sign of the derivative could change. It doesn't in this one, but it could. So I need to include that too, just so that my sign chart for my derivative is still right. So I pick a number larger than 4, like 5, it's positive, positive, positive. And then I pick a number between 2 and 4, like 3, it's positive, negative, positive. And then pick a number between 0 and 2, like 1, it's positive, negative, negative squared, still positive. So positive, negative, positive is negative. And the pick a number over here that's negative, it's going to be negative, negative, positive. This function is increasing, decreasing, decreasing, increasing. So I have a relative maximum of 0, I have a relative minimum of 4. And I don't have any relative extreme at 2, not because it's negative, negative, although that's also a reason, right? If it's decreasing, decreasing, you don't have a relative extreme there. But it's also because I have a vertical asymptote here. Like the graph of this function has a vertical asymptote at 2, and it is increasing until I get to 0, decreasing afterwards, decreasing afterwards until I get to 4, and then increasing afterwards. And this is like 4, 8, and this is 0, 0. So what I'm trying to emphasize here is that even though x equal to 2 isn't a critical value, since the derivative is undefined there, it's still important that it shows up on the number line for the sign chart of your derivative. All right, we will definitely talk more about this on Monday. But I think that's a good start for you guys working on your homework, because I feel like, let's see, so we didn't cover question, we didn't do the second derivative stuff, but the second derivative stuff is kind of the same. But yeah, the rest of it, yeah, problem 9, you guys will go to problem 9, no problem. Yeah, so I think you guys should be able to get a good start on your homework. If you have questions, you're welcome to start a discussion on Canvas or send me an email. Here is the attendance stuff again, and please fill out the attendance as usual. And have a nice, oh, I won't see you guys on Monday, right? We have a holiday, Memorial Day, so I will see you guys on Wednesday. So please do feel free to send me questions over the weekend. So since it's a long weekend and we won't see each other on Monday, and you might have questions before then. I definitely recommend starting a discussion on Canvas. That way everyone else can see my responses to what you write. So yeah, have a nice long weekend, and I will see you all on Wednesday. Bye.